continue the discussion for propulsion. And where did we stop? Okay, we wanted to find H4, right? Yes, H4. So we and this is essentially a part of a quiz, right? So you guys have to come up with the idea. Do we have any questions? Do we have any questions about what happened on Monday? No? So everything's clear? Okay, let's continue. So what do we have when it comes to H4? What do we have? H4 is here, essentially after the pump. And as you can see, the pump's process is supposedly an isentropic process as well, right? Is it H4? What are we looking for? H4. Yeah. H4. So any ideas? Do we have H3 though? We haven't found H3, have we? No, we don't have H3. So we have to first find H3. What should we do to find H3? What was the information that was given to us? It was we found it from the chart, right? Yeah. So we went over the H3. I don't have it on my note, but that's why. So what should we do? Let me actually open up the table. Your homework is uploaded, but the deadline is what happened? What? Deadline is going to be in 2 weeks. The due date is going to be in 2 weeks. Because I originally, for whatever reason, I wanted to give this homework. I wanted this homework to cover the power cycles, but we are going to finish power cycles in 2 weeks, not next week, right? So I need to give you more time on the homework. But the homework is already uploaded, so you are going to have 2 weeks to answer the question. There are 4 questions on the homework, 2 of them from vapor power cycles, which we are talking about today and we talked about on Monday, and 2 of them are going to be on gas power cycles, which we are going to talk about next Wednesday and also the Monday after it. Okay? And today our main focus is going to be on solving some problems. So we have the tables now. Are we recording? Yes. Okay. Any ideas? What should we do with H4? Think about it. Work done by the pump is going to be equal to m dot H4 minus H3, right? We can take the m dot to the other side. But do we have the work done by the pump? No. Do we have m dot? No. What should we do? Any ideas? Think about it. Is there any other way, is there any other formula we have that is going to help us calculate it is going to, is there any other formula that is going to help us calculate, find the work? We have talked about this. Think about it. Is there any other formulas that is going to help us do this? I'm sorry. When we were talking about the first law, what was the formula we used to calculate the work? It was related to pressure and volume. Do you remember this? Work is equals to the integral of P dV, right? Right? The correct way of this formulation is actually the integral of d PV. So for an isobaric case, it's going to turn to P dV, because this is, let me actually expand this first. This is going to be P dV plus V dP, right? When dP is 0, the integral is going to be integral of P dV. When dV is 0, it's going to be an integral of V dP, right? So keep that in mind. So as Drew, right? Drew said the formula we have is actually the integral of P dV. Can we use this to our benefit at all? Think about it. Is the volume going to change here? We are pumping water. No. What about pressure? Pressure is going to change. Okay? So the equation we actually going to use is the integral of V dP. Right? And we are going to assume, that's a very simple assumption, we are going to assume that the changes in pressure are linear. What does this mean for the integral? Constant. Your derivative is going to change to delta, which means that your integral is going to be essentially V delta P, right? The changes in pressure. So P3 minus P4, or P4 minus P3. Sorry, P4 minus P3. And this is also the volume at point 3 or the volume at point 4. Doesn't really matter. And keep in mind that this is W dot, right? So we are talking about the power. If we divide this by M dot, is going to be the specific volume, P4 minus P3. Okay. Can we read any of these parameters from the tables, or is any of these parameters given to us? Can we read the specific volume at point 3 from the tables? We read the entropy, we read the enthalpy. Why can't we read the specific volume? We can, right? Yes or no? Why are you guys so confused? Are you confused, or what is going on? You're fine? Everyone's fine? Okay. We didn't do this. You guys, we didn't do this last lecture, did we? No? Why are you guys so, it looks like you guys are not clear on what is going on here. So we need to find the properties of saturated water, right? Which table was it? Was table A3, right? Temperature, pressure table, right? Yeah. What is the pressure at point 3 at the state state 3? What was the pressure? 0.0008 pascals, right? 0.008 megapascals. 0.008. How much is that in bars? 0.08 bars, right? So we're gonna look at this. And what are we looking? We are looking for the specific volume for a saturated liquid, because we are after the condenser, right? The station 3 is after the condenser. We only have saturated liquid. So 0.08, this is the value you're looking at. And then let me just make sure I'm reading the correct value. Yes. This is the value you're looking at. 1.0084. Yes. That's right. That was the next thing I wanted to talk about. So your correct value, because what it says here, these values are already multiplied by 10 to the power 3. So the values you're going to use, you have to multiply them by 10 to the negative 3, right? That's just a regular table value. So it's going to be 100.8. 1.0084 times 10 to the negative 3. That's the specific volume. What else do we need here? Do we have the pressures? We have the pressure at 0.3 and 0.4. We have one, yes. What are those pressures? Okay, do we all agree on this, or is there any opinion that differs from this, huh? So do we all agree that this was given to us, right? Just plug in the pressures. 8 megapascals at a P4, 0.008 megapascals at 0.3, and nu 3 was 0.4 times 10 to the negative 3 equals to W dot divided by M dot. So we can find this value, right, and set it equal to the enthalpies. We have already read the enthalpy at 0.3. For the saturated liquid, we can find enthalpy at 0.4, right? And based on my notes, enthalpy at 0.4 is going to be equal to 181.94 kilojoules per kilogram. Is this clear? So we already have H1, we have H2, we have H3, and we have H4. We have all of the enthalpies we need to have. Okay? Next part is we are asked to find the thermal efficiency. How do we find the thermal efficiency of this cycle? So what was your name? Zach. What Zach is telling us is that H3 minus H 1 minus H3 minus H4 divided by H4 minus H1.
And then H2 minus H3,
Okay. Is this the correct formula? Do we all agree? Okay. Is there any other method we could have used here? We could have just calculated the W of turbine as well, W of prime divided by Q dot in, which is H1 minus H4 multiplied by M. But we have all of these values. We can just plug everything in and get the efficiency. Let's see what we can find from the efficiency. Let's see if we can all find the same value for the efficiency. I want all of you to calculate the efficiency based on the given values. I want to see all of you using your calculators. Yes. H3, I have to go back to the table, but we have the table here. So saturated liquid, H3 173.88. H2, I can actually look at my notes. H2 is going to be 1794.8. H2. If you don't have H2, 1794.8. So we have all the parameters, and we only want to find the efficiency. Whoever gives me the correct value first will get a bonus point. And it's just a division and subtraction, yeah? 37.1, yeah. So Igor, I've given us 5 bonus points already, but I haven't updated the Blackboard. So if I have told you that you will receive a bonus point, send an email to me so I can update it tonight, right? Okay. Thank you. Yeah, it is the efficiency is going to be 37.1%, as Igor said. What is the next thing that we are asked to calculate? Is the backwork ratio. How do we calculate the backwork ratio? W dot of P divided by W dot of turbine. H4 minus H3 divided by H1 minus H2. So plug the values in. Let me actually plug the values. 181.94 minus H3. What was H3? Pardon me? 173. 173, yeah. 173.88 divided by, what was H1? 2758. Thank you. 0.8. 1794.8. Your backwork ratio is going to be equal to around 84%. So 0.84. Let me ask you this. What does this mean? What does this backwork ratio mean actually? Think about it. What does it represent? Yes.
It's the amount of the work that comes out of the turbine that has to go back to the pump.
Exactly. Right? You can actually see it on the equation. That's the ratio between the pump's work required by pump and work generated by, or energy generated by, power generated by a turbine, right? So here we are actually using 84% of the work we generated by the turbine to work the pump, right? That's a lot of energy, right? That's a lot of generated energy, but there is no way around it. We have to do this, right? We have to put this back to the turbine. What is the next thing that we are asked to find? The next thing is mass flow rate. How can we find the mass flow rate? Any ideas? Mass flow rate? What is the other parameter that is given to us other than the two pressures? We were given two pressures, right? Net work.
And that's equals G time.
And that equals to what?
That equals. I'm not sure about my performance.
That's all right. So that's W dot of net. What is it equal to? Not the value. What does it equal to as like the equation for it? Work by turbine minus work by the pump. How do we calculate the work by turbine? M dot multiplied by H1 minus H2, right? How do we calculate the work by pump? M dot multiplied by H4 minus H3. We have all the H's, and we were also given the W dot nets, right? Plug in all of the values. You should be able to find the value for M dot, which based on my notes, it is 300.77 multiplied by 10 to the power 5 kilograms per second. The next thing we are asked to find is Q dot in, which is simply m dot, that's the Q dot at the boiler, m dot H2 minus H3, just plug in the values. The other thing is the Q of condenser, whatever heat we have removed from the system in the condenser, which is, I'm sorry, this is H1 minus H4. Why did I say H2 minus H3 is Q out. If you plug in all of these values, you should be able to find the solution to your problem. Okay. Any questions so far? So there is one last part to this problem. We are asked to find the mass flow rate of the cooling water, right? So that condenser is actually a heat exchanger, right? The hot steam or hot mixture is coming in, right? And the saturated liquid is going out, right? On the other side, we have cold water coming in and then hot water going out, right? These are two separate systems, right? So make sure not to confuse it. This is a different water. This is not your working fluid. It's the water that is responsible for cooling your vapor, right? That's the part D. That's the last part. We are asked to find the mass flow rate of that cooling water. And that mass flow rate that can give us these values for H2 and H3, right? How can we calculate this? Any ideas? Think about it. We are given two temperatures. So the water, cooling water, I'm going to say TCW in is 15 degrees. And TCW cooling water out is 35 degrees Celsius. And we want to find the m dot needed to provide this much heat removal capacity, right? Q dot out. What's that? 35. Any ideas?
So we have Q out, right?
What's that?
We have Q out, that's what we said.
That's what we just calculated, right?
So we just use the table, change the temperature, and then find out
Okay, that's a very good thing you brought up. So this, which tables? You have to speak up. We don't have a saturated water, do we?
We say that Q out is equal to mass flow rate of the coolant water times the specific heat of water times the temperature of water.
That's something you can definitely do, right? But the only thing needed here is the specific heat of water. You can assume the specific heat of water is just a regular specific, because the temperature is like 15 degrees Celsius, 35 degrees. So we can just use the specific heat of liquid water we always use. Does anyone remember the value for it in SI? Kilograms Kelvin, yeah. So 1.48 or 4.18 or 4,000. They usually run it up to 4,200. 4,200 joules per kilogram Kelvin. Right? That's an assumption we are making here. We are making that the C does not change. So in reality, the equation Q out is going to be Q dot of the cooling water, that they have to be equal because they didn't tell us about any losses in the heat exchanger, right? Do we know what a heat exchanger is? Because none of you have passed heat transfer except for Nicholas, right?
I'm in it right now.
You're in it right now. You have passed heat transfer, right? So what is a heat exchanger? You didn't learn about heat exchangers? Who was your teacher? You didn't learn?
I don't remember.
Huh?
I don't remember the heat exchanger.
You don't know. So who can tell me what is a heat exchanger? Just you don't have to explain things. Yes.
Just like a radiator, using that transfer
Like a radiator.
system.
So
It's something that like takes heat out of the liquid into itself.
how does it do it? You can just speak up. You don't have to ask for permission.
I'm assuming it's like a fancy heat sink that allows heat to transfer freely in and out. And it's got a cold side on one side, and heat's going to escape, or it's got a hot side on the other one that's going to be heating up the liquid on the other side.
Fancy heat sink. That's very interesting. But so it is essentially a radiator, as Drew said, is a heat exchanger. But the most important part of a heat exchanger is essentially that you have fluid in two different pipes. Right? They can move in like different directions. They can move in the same direction. Doesn't really matter. You can have fluid crossing over another pipe and the fluid moving inside the pipe. The point is these two fluids shouldn't mix with each other. That's the point of a heat exchanger. So you have two, like in a radiator, you have cooling water inside those, inside the fins. Thank you, and you have air passing through that water, right? But the water and air don't mix. Right? That's the idea of a heat exchanger. So in condensers, usually that's what we have. So we have. Let me just finish this thought. We have the cold water coming in, right, and going out. This is the regular condenser, insert. And then we have the hot steam or mixture of vapor and water, liquid water, coming in and going out from the other side of it, right? The heat that is being transferred between the two is essentially the energy transfer. Whatever energy we lose here is going to be added here, right? So there is this energy balance. Does it make sense? Okay. What did you want to say, Nicholas?
Can it be like the two same fluid?
Yeah, that doesn't matter. They shouldn't mix. That's the only thing. And it makes a lot of sense. You cannot just add you can, but that's beyond the point. It is not going to be a heat exchanger if the two fluids mixed, right? We are not going to call it a heat exchanger. Okay, so the two Qs are the same. Whatever heat we have removed from inside the condenser, from the vapor, from the working fluid, is going to be added to the cooling water. Right? Well, how can we calculate the heat here? The original formula is going to be m dot h of the cold water inlet minus h of the cold water outlet, right? So h at this 15 degrees and h at 35 degrees. If we assume that C doesn't change with temperature, which is the assumption we usually make, is going to be m dot C, T cold water in minus T cold water out. And again, this is just a sign convention. Make sure you are consistent with the signs, right? So this is how we usually do it. But let's say you don't have the C and you are not told to assume C is constant. What can we do? Zach said we have to look at the tables, right? But which tables? That's the golden question, right? Can we look at the table A3 here? We don't. So it can, yes.
Would you be able to like assume that it is because of the temperature range that you're in?
Why would you be able to assume that it is? Because its pressure has to be the same pressure, right? You are essentially assuming a pressure that doesn't really exist,
Yeah.
right?
So we're not assuming that the pressure in the cold water tube is the same.
It's not like 8 megapascals, 8 megapascals.
No. It's a different system, yeah.
Is there any evaporation happening in the heat exchange?
I don't think so, but we are not told anything about it. We had the equation, right? We had the question. It didn't talk about evaporation. One thing we can do is to look at this temperature table. And this is not something I like to do, and a lot of books don't really agree with this. But this, especially Moran book, which is the book we use as a textbook here, does this, right? It's pretty close to the real answer, right? I usually would rather assume that C is constant and go that route, or like read the C from a table or whatever, right? But what you can do is that you can read the enthalpies from this saturation temple. The difference between the enthalpy is going to remain constant. Does it make sense? So the real the enthalpy itself is not going to be the same as the saturation enthalpy, right? But the difference between the enthalpy, that's the claim your book makes, right? It's going to remain the same. As long as you are dealing with the enthalpy difference, you can come to this table 2, A2, table A2, not this one, table, the temperature-based table, and read this. Yeah. Read the temperature values, subtract the two values, and use that subtracted value. That's a very important part. Okay? Does it make sense? Okay. But again, I would rather you just tell me that I assume the C is constant, found the C, or read the C from a table based on temperature values. Right? And this is the, I would rather you do that. Right? That's going to be less confusing, and you're not going to confuse your working fluid. So, but you will get the points if you don't do that in an exam or homework, right? No matter what. Any questions? Okay, so this was supposed to be your quiz. And a problem like this, you will definitely get on an exam. Maybe a little, even a little more complicated, right? So you have to make sure that you can solve this, because there will be other problems on the exam that you need to take care of as well. So make sure you're ready for this type of problem, right? And all of propulsion is cycle analysis. Most of propulsion is cycle analysis. It's going to take a long time to do the problems. Yes?
How many sections on average are there going to be per problem on the exam?
What's that?
How many sections on average per problem? Like part A, B, C, D,
how many sections? So, I don't know. I haven't designed the test yet. I don't know. That's a very...
Just don't want to see half the L. They don't.
It is not going to be like the fluid mechanics exam. Okay. That's for sure. I'm hoping it's not going to be like the fluid mechanics. I think all of us are hoping for that. Because I don't want to give... if it was something like this, I will make it a take-home test. Right? So you can just go home. But it's going to be a hard question. So it's always a... You like a take-home test?
More time doesn't feel stressful.
More time?
More like being
Believe me,
careful
take-home test. Take-home tests are... What's that?
That just makes it a hard problem. So you be careful what you wish.
Yeah, that's I would agree with Igor, because I mean, don't worry about it. You already had a course with me, so you know your exams may be intensive, but at the end of what's that? You got a good grade though out of the course, didn't you?
I got like
Okay, that don't worry about. I don't want to talk about it. I don't remember them.
I don't remember.
Yeah.
We could ask you in person. That's a lot more powerful than people think.
Yeah, that's I agree. I mean, take-home tests are gonna be easier for me but harder for you. That's for sure. Okay, so let's continue. We want to finish this vapor power cycle. So today we just have a very small part that we need to discuss, and then we are going to solve another problem. This problem I'm going to ask you to solve completely by yourselves without any help from me. Okay, and whoever solves this will get a bonus. Whoever solves this in a timely manner. So let's get to the thing. One thing that we need to discuss is that let me actually skip these. How to deal with the irreversibility of the processes. Like there are two processes here that we are assuming are reversible, are isentropic. But in reality, no process is isentropic, right? We will definitely have some entropy change, right? How can we include that in our analysis? It's actually pretty simple. We are going to, and the turbine manufacturers and also the pump manufacturers, all of those, have already calculated this. So whatever pump or turbine you buy, you already should know the turbine or pump's efficiency. So efficiency of turbine, efficiency of the pump. And this is going to be the help we need to calculate the efficiency, to include the irreversibility of the process. We want to include the irreversibility of the processes, of the turbine and pump processes. So for eta of turbine, efficiency of turbine is going to be H1 minus H2 divided by H1 minus H2S. This S refers to the isentropic enthalpy. So the method we used for the previous example is actually going to give us the isentropic enthalpy for H2, right? So we found the isentropic enthalpy, we had the H1, If we were given an isentropic efficiency of the turbine, we just plug it in here, and then we can calculate the actual enthalpy after the turbine. Okay? What about the pump? What do you think is going to be the pump efficiency equation? So we have H3, for pump we do H4 minus H3, right? So you are saying H4 minus H3 and H4S minus H3, right? Is that what you're saying? Do we all agree on this? Yes? No, that part is true because the irreversibility comes into play after the pump, not before the pump, right? Even then, with turbine, we are doing work on the surrounding, right? So it is the reverse of the pump. But station 2 is after the turbine. Station 4 is after the pump. So the reversibility comes into play after the process is done, not before, right? Okay, that is not true. This equation is not true. The equation for the pump's efficiency is actually H4S minus H3 divided by H4 minus H3. But why is that the case? Why have we reversed this? What are we going to achieve with a turbine? We are going to produce some work with some expansion, right? The irreversibility is going to mean that we are going to have the same expansion, but we are not going to produce as much work, right? So delta H actual, which is the work generated by the turbine, the power generated by the turbine, is going to be smaller than the isentropic one, right? What about the pump? What does irreversibility in a pump mean? Go ahead. you are going to need more work compared to a reversible process, right? So an irreversible process for a pump means that you are going to require more work from the surrounding, right? But an irreversible process in a turbine is that you are going to receive less work from a turbine for the same expansion. Does this make sense? So it's, essentially they are moving in different directions. They are reverse of each other, right? That's why the equation are reversed. So make sure you understand this, so you are not gonna you don't get confused when you are solving a problem. And these kind of design problems, if you end up designing a jet engine, these are the type of analysis you will do, right? These are pretty simple analysis, table reading, right? There is no like partial differential equation that needs to be done by a computer. You can just read the table, like do this analysis. These are called the system level analysis, right? This is something, there's a lot of software that can do this, but this is something an engineer definitely needs to do when it comes to like aerodynamic design, right? So make sure you understand. Yes?
You want a higher entropy pump in order to increase efficiency of the pump?
You don't want a higher entropy. The isentropic entropy, the actual work. Efficiency is always less than 1, right? The actual work is going to be more than the isentropic work, right? The actual work you need to do this, to pump this. That's so, and you want to keep this smaller than 1, so the isentropic work is going to be on top. Isentropic work is always smaller than the actual work. So, in the previous example, what we did was we actually found, with the methods we used, we actually found the isentropic enthalpy, right? If we were given a pump efficiency, we should have plugged all of the values in to find the actual enthalpy, right? Does this make sense? Okay. So let's move on. And the example I'm going to give you is actually going to be the same example as you solved. The only difference is going to be you will be given two actually efficiencies for the pump and turbine. So you have to do the same analysis, just have to include the turbine efficiency, right? But before working on that example, I just want to mention some things about improving the performance. I'm not going to go into that much detail with this, and you are not going to see these type of calculations in an exam or in a homework, mainly because it is very much more thermodynamics focused than like propulsion focused. But you should know this. Okay, there are many different methods that we can use to increase the performance of a turbine. With all of those methods, we are going to lose some things. So these different methods are used at different places because different things are going to be important, right? At different applications. We're just going to go through all of these applications one by one, or all of these methods one by one, but I'm not going to go that deep on them. The first method is the superheat. So you are going to use your boiler to superheat the vapor. What does a superheated vapor mean? Essentially, when you have saturated vapor for water at 1 atmosphere, your saturated vapor is at 100 degrees Celsius, right? Superheated vapor is a vapor that has that is like 110 degrees, more than saturated, 120 degrees, right? Which means that your boiler has added more energy to the vapor, right? So when the vapor goes to turbine, you can extract more energy. That's the idea. You can extract more work out of the turbine. That's the idea. But the problem is superheated vapor may cause a lot of problems with the turbine blades, all of those things, right? So you have to be careful, and you have to know the correct application to use this. The other method is the Reheats method. That means that we are actually, let's draw the cycle, the Rankine cycle. We have the boiler, we have this is going to be your station 1 that goes to the turbine. Then the turbine is going to have 2 different sections. This is something you are going to see many, many times actually. This is a very popular method of increasing performance. And we take some of the vapor that is coming out of the turbine, take it back to the boiler, heat it up, and then take it to the turbine at the station 3, and then we send it to the condenser. 4, 5. Station numbers are going to be different then, right? Because we have added like 2 more processes. Essentially, you take the vapor to the turbine, you extract some of its energy, you take it back to the boiler, that vapor, that like mixture, whatever that is, heat it up, saturation or superheat vapor, take it back to the second station of the turbine, and then, yes?
So after the first turbine, then, does that go into the second one, or is that just, like, does part of it go into the second one as well, or?
It doesn't go into the second. But turbines are connected to each other through a shaft, right? So the process just comes out of the turbine. Right? Probably it was better if I just used this instead, yeah. Any questions? This process is called the reheat process. It can increase the performance a lot. And so, what do you think is going to happen to the TS diagram of a Rankine cycle? So we have this, right? The regular TS diagram of a Rankine cycle was like this. This part of it, it's just the real. Let me give you the real Rankine cycle. A little superheat and then comes down here. Okay? What do you think is going to happen if we add this additional reheat process? This is this location, right? This is just after the turbine, and we are losing some energy. We are expanding, we are losing some energy until we go out of the turbine. The idea here is that at some point here, at some point in the middle of this process, we are taking vapor out of turbine, reheating it, right, and then expand it again. Yes?
You do it multiple times?
Yes, you can do it 10 times. But the reheating process itself needs some energy, right? So you're adding the energy required as well. There is always a compromise, right?
I know we had the issue with the liquid vapor mix in the boiler. Is that an issue as well?
Liquid vapor mixing, what was the issue with that? Was in the pump, not in the boiler. I'm talking, I think you're referring to it.
Is there a condenser?
Condenser is here, right? It is actually, condenser is going to be here. It is actually inside. You have to design it in a way that is inside this, right? Condenser is here, and this is here where your pump comes in. It has to be saturated liquid. Okay? Again, saturated liquid on this line, saturated vapor on this line, and mixture here in middle. And outside of the lines we have superheated liquid and superheated vapor, subcooled liquid.
You don't have to have a pump to pump it back into the boiler once it's already from like first. So between the first and 2 on our diagram right here, you want to pump it back in there. You want that pump.
Let me ask you this then. What is the mechanism that causes a flow to happen? Pressure difference, right? As long as the pressure after the turbine, you design the pressure after the turbine to be higher than the pressure inside the boiler, you don't need a pump, right? So as long as you're taking the vapor at the correct location and you're sending it into the correct location at the boiler, then you should be fine, right?
So do reheat systems have to be superheated?
I guess that's a very good question. I guess it is a better idea to have it superheated, but I've never thought about it actually. It doesn't have to be super. Whenever I've dealt with this, it was superheated. But this question never crossed my mind. I never asked anyone, I never read it.
Is that how they achieve the pressure so that they don't need a pump?
That's probably a good way to think about it. I can't really give you any definite answer because I haven't thought about it, but that's probably a good way to think about it. Yeah. Any other questions? Okay, let's see how many more. Yeah, and as I said, we are not going to have any questions with this reheat cycle. There are other cycles that we are going to see in the Brighton cycle analysis, the gas cycle analysis as well, the cogeneration, all about the other methods. We will talk about those a little more because that's the focus of the course. But this, as long as you're familiar with these concepts, you should be fine. And the analysis part is actually not going to be any different. It's just has more steps, right? So you need to do more work, I guess. Okay. Any questions? If there's no question, let's get to the example I want you to work on. We're already 3:14. We probably need to work through this together as well. Depends on how well you perform, right? Has any of you studied the PowerPoint? Not yet? No one? Okay. That's alright. If you had studied the PowerPoint, then you would have a solution to this, right? Because the solution is already there. Right. So this is example 8.2 of the book. We want to reconsider example 1. The only difference is going to be that we are going to, in our analysis, we are going to include the turbine and pump efficiencies of 85%. Let me go back to the example 1. So you already know what you are given in this problem. I'm just gonna go to the original question. So you have whatever you need. Everything is the same. The only difference is that you are going to have turbine efficiency and a pump efficiency. So we are including the irreversibilities of turbine and pump. Does anyone know who else registered for this class? Lawson. Other than Lawson. But there are 14 people registered for the class, but you are the only one who has showed up in the past 3 lectures. Emery didn't show up as well. Is Emery going to graduate?
I think so. He's done the electrical track, so he should be fine.
Was it Whitman's class?
What's that?
Was it Whitman's class?
Yeah, that's probably it. Yeah, that's right. Yeah. Okay. I should definitely. guess let me stop the recording.